So thank you for the invitation to be the moderator of this session, and thank you for the speakers that we are going to see some of the presentation and results of their work together. So thanks all to MIT Portugal program to organize this conference and to support a lot of work that we are going and saw in the last sessions. So first we have we're going to have two presentations and then a brief session of discussion. We have actually two joint presentations. First will be Anna Pires, so a researcher at the Center for Robotics and Autonomous Systems in ESCTech. And at their center, they are going to join and present something that I don't have the name now. I don't know why.
We will let you know. We will let you know.
Sorry.
Don't worry.
And yeah, you have 50, 20 minutes, so please, and then we follow up with the next.
Can we start?
Yes.
Thank you.
Thank you, Anna.
Thank you so much. Hi, everyone. So, good afternoon. Thank you so much. It's an honor to be here, to be on this stage, to share the stage with our moderator, with Vasco, Carmen, and my student. It's an honor to share with you this stage. So I'm Ana Pires. My colleague is André Santos. We are both researchers at ESCTech's Center for Robotics and Autonomous Systems, and we would like to thank to MIT Portugal program team all the support. Thank you for this opportunity to present our work, and congratulations on this initiative and for all the organization. So the project is about Sentinel Orb system, about this amazing scout robot that is being developed. And as you can see here, the project envisions the future human spaceflight and robotic exploration in 3 destinations, as proposed by ESA, by the European Space Agency. So, low orbit, International Space Station, and Moon or Mars. This we can dream, right? So this is the dream. we hope one day have to be able to see our robot to work and to be capable of working in these 3 types of dimensions. And of course, inspired by the ocean to near space topic, the rationale of the project comprises the space-sea interaction, working in extreme environments, and to understand the similarities and also the differences between underwater environment and microgravity environment. And why? Because in our robotics lab, our expertise and our core is underwater technologies. This is one of our underwater robots, our underwater autonomous vehicle, and Sentinel Orb is an exploratory project focused on developing a smart orb, a small sphere, inspired in our underwater autonomous system, our UAV UX1 Neo, one of the most powerful and evolved autonomous systems, underwater systems, and with a vertical approach. This vertical approach from deep sea to outer space aims to develop this service robot for assistance and cooperation, and to cooperate and to help us in these 3 dimensions that you see here. This could be possible application scenarios that our Scout robot could operate in deep sea, in extravehicular activities, and in near space, in debris, in monitoring or collecting debris, etc., helping us and supporting in these 3 scenarios of application. So, This was the rationale, this was our motivation, and the main objectives of this project are, like so many spheres that you already know, like the Astro Bee from NASA, developed by NASA, the Int Ball developed by JAXA. So we want to miniaturize, inspired by our UAV and the water vehicle. We want to miniaturize the design and to develop a system based in this underwater system. Then integrate sensors and give the ability to fly and to navigate. Use visual inertial odometry with high resolution camera, and of course test space maneuvers in microgravity environment. And how? Ultimately, our goal is this one. We want to do a parabolic flight. We want to prove the concept. We want to test our Scout robot. We want to test the performance of our Scout robot. We can dream to go to space, but unfortunately, this is only an exploratory project. That's why a parabolic flight would be enough for us to prove the concept and to test the performance of our Scout robot. Scout robot. So this is an example, a parabolic flight that was carried out at the National Research Council of Canada, and hopefully we will be able, and ultimately we will be able to prove that our Scout robot can work, and the capabilities of our Scout robot, of our Sentinel. Of course, under the scope of this amazing program, we have two students, João Coutinho. João Coutinho is finishing his degree. We also have André Santos. André Santos is working under the scope of Sentinel, under the scope of this exploratory project. He's finishing his master's thesis. So I couldn't be more proud of them. And of course, they already had the opportunity, the amazing opportunity to present and to display this project at the GLEX Summit, the Global Exploration Summit that took place this year in June in Porto City. So they already had this possibility. And now, after talking about the motivation, I will pass the word to André Santos. André Santos will now focus on the technical parts, but it is his first time on this kind of events and this kind of stage, and in an international conference speaking in English. So let's give a big round of applause to give motivation to André Santos. André, the floor is yours.
Thank you, Anna. Hello. Thank you, Anna, for the... Oh, yeah, I need this to skip the slides. Okay, thank you. So I'll try to dive into more the technical part of things. So initially, I want to just dive into the motion system that we're developing. We want to integrate a similar configuration that we have in the UX-1 Neo underwater vehicle. And it is composed of two sets of 4 propellers. And we want to adapt this configuration to our Sentinel-R project with 2 sets of 4 thrusters. So instead of having the propellers, we want to change to thrusters due to the lack of in the space exploration, there's no atmosphere, so there's no propellant for the propellers to work. So we require a propulsion mechanism to operate under those circumstances. Also, one slight adjustment that we wanted to make was we wanted to shift slightly the orientation of the thrusters so that we can enable a lot smoother rotational movements. And we wanted as well to orientate the thrusters at a 45-degree angle so that we can maximize the forces between two axes. Okay, so regarding the system overview, this is our full skeleton. There's a legend over there that has all the components listed. The main overview that starts with an air reservoir that has an accumulated pressure of the container with a lot of gas. Then we have a pressure regulator and a filter. This pressure regulator is responsible to drop the pressure to the rest of the system. We do that because we want to store a lot of pressurized gas in the initial container so that we can achieve higher operating times. And in the rest of the season, we only want to operate on low pressure levels, like 2 bars. So that's why we have the filter and the pressure regulator. Then afterwards, we can connect it using fittings and tubings. We can connect it to two manifolds that each contain 4 solenoid valves that are controlled by the main board, the voxel 2 main board that I will mention afterwards. And also another thing that I forgot to mention, the gas type that we're considering for this project. There are a plenitude of gas types that are adequate for this, but since this is only an exploratory project and we only have, it has to be a non-toxic gas, so regular air or CO2 does the trick, but we want to introduce CO2 for its lower mass. And as a final note, we just have to consider all the components that are electrical, and we need to dimension a battery that is capable of powering every component. Okay, regarding the visual inertial odometry, Voxel 2 flight deck is the main board that's designed for this project because it has an advanced flight controller that's called PICSOC4, and this controller is responsible for having inertial measurement units, or IMUs, and that collects the data for the orientation and calibration of the board. Then we also have a module for Wi-Fi that's pretty useful in lab testing and debugging, so that we can connect to the host machine. We also have an expansible board so that we can connect our peripherals to the main board. That's the expander board. And there's also 6 cameras that we have in place. We have 2 tracking cameras and 2 front and back stereo image sensors. They are high resolution cameras that we wanted to disassemble this original kit because we wanted to attach the cameras to the external shell of the project. Okay. The web portal is a really great tool that's provided by Model AI. That's a web server, an embedded web server that enables camera inspection and has a lot of debug tools that we can use to test our project. And it's broadcasted on Voxel's 2 IP address. This web portal showcases the video from the selected cameras. We can selectively close or open the video feeds, and we can integrate machine learning and computer vision algorithms that we can detect objects around us. Another great thing about these debug tools is that we have a plotter. We have an IMU plotter that we can graph automatically the values of the orientation and acceleration in certain axes. Another thing that we wanted to utilize the cameras for is the visual inertial odometry, which means we need to calculate, we need to estimate the velocity that we're receiving through each puff of air. So for instance, we're going to have a thruster that's a small nozzle that will have a pressurized airstream, and we want to establish a relationship between that single puff of air that provides thrust force to the velocity that it brings and how much the sphere travels. So with that in mind, we can do that by referencing data points and the objects around the environment, and then we can establish like a database. And according to that database, we can predict how closer we are to the relative objects around us, and we can predict the velocity. So, and in space, where GPS is unavailable and a lot of connectivity gets a lot worse, this visual inertial odometry for Voxel allows for autonomous navigation by referencing stars, planetary surfaces, or space station structures. Okay, so I just want to quickly mention what's our current situation in this project. Right now we are assembling and lab testing our components, and we just now ordered as many off-the-shelf standard components because we want to reduce development time. So on the right you can see our compressed air tank that has a socket that we can plug it in and feed the tank whenever necessary. It's really useful for testing. And we have also our pressure regulator and our digital sensor. Oops, sorry. Then we have our manifold and the valves, and all of this is in comparison to the UX1 Neo. That's a UX1 Neo miniaturized version, and we hope to achieve a similar design. Afterwards, we're designing in CAD that's external shell and all the supports required. In the top left, you can see some hands-on approach that we're taking data from the IMU plotters that I mentioned previously, and in the bottom left, it's a custom-built box that we developed because we had to disassemble the original box that came with the voxel. So yeah, that's one thing that we were working on. So thank you for your attention. It's been a pleasure. And we were really looking forward into doing a parabolic flight really soon. Thank you. Okay. I can now also answer your questions. I don't know if I should be sitting down or up.
Maybe in the final we can have a space.
So I guess it's okay. I leave this here. Thank you. Thank you.
Yeah. Thank you, Andre. Yeah, you don't be so, or you don't look so nervous. So
I don't know what just happened. I was extremely nervous, but suddenly.
So now we have with us Carmen Garcia and Vasco Guerra that they are going to present the plasma-assisted CO2 recycling, addressing climate change on Earth and enabling life on Mars.
So, thank you, Renato, for the introduction. So the first thing, I was quite nervous for this two-person act, but it sounds like it went great for Anna, Andre, and Cadence and Helder. So that made me much calmer. My name is Carmen Guerra Garcia. I'm an associate professor in the Aeronautics and Astronautics department at MIT, and I'm here with my colleague Vasco Guerra from the Instituto Superior Técnico. We're not related, even though we have the same family name. The presentation we've put together is about the technology we're developing, but it's also about the collaboration we've established thanks to this MIT Portugal project. I didn't know Vasco before getting started. I had the idea of utilizing plasmas, that's our expertise here, for Mars in situ resource utilization, basically utilizing the Martian resources to create valuable products. And I said, like, someone else must have thought about this idea. I Googled, and Vasco was the only one who had thought about that idea. So thanks to this framework, I contacted him, and I think this was back in 2021. Since then, we've had a very fruitful collaboration, and it's been a true pleasure having those interactions that have permeated from us to also a series of students and young researchers. Tiago Silva, he has been instrumental for this collaboration. He actually became a Fulbright scholar after the fact and joined my group for a few months. Lainey McKinney is one of my amazing graduate students who has been very active and has been traveling back and forth to, and my colleague Ahmed Ghanem, who brings expertise in a different technology that I'll briefly mention for our final product. So
just brief words about our group at Técnico. We are at the Institute of Plasmas and Nuclear Fusion. The N prime group, prime is reactive plasmas. The N is sort of a secret, but if you read the description, you will understand what it is. Our group explores the potential of non-equilibrium low-temperature plasmas for tailoring energy and matter at nanoscale level for reaching new horizons in space exploration. So it has multiple meanings because we are organized in 3 teams inside the group. The Hypersonic Plasma Laboratory, with the shock tube to make entry studies, atmospheric planetary entries, and related to space exploration. The Plasma Engineering Laboratory, the nanoscale, focusing a lot on the production of graphene. And the plasma modeling on simulation, trying more fundamental studies to understand all these non-equilibrium properties of the plasma. So I'm in fact the head of the plasma modeling and simulation, and my colleague Tiago is also working on the modeling and on the experimental side.
And my group is sort of a little bit parallel. This is just a zoom in inside the aeronautics department, the aerospace plasma group. We are working with gas discharge physics, fundamentals of electrical breakdown for different applications in aerospace. So we're working on varied topics from lightning safety to wind turbines, aircraft, to plasma-assisted aerospace technologies, and that's where this collaboration really falls in. Plasma reactors for chemical conversion, for sustainability applications, but also thinking at large of going to other planets and having means of creating valuable products there. So what is the focus of the problem? We've been hearing a lot in the conference about oceans. This project is more in the atmospheric side of things. Earth, like you know, it's made up of nitrogen and oxygen mostly, but unfortunately we have a teeny bit of CO2 that causes a lot of trouble. So eliminating those CO2 sources is of course very important, but utilizing those CO2 for valuable products is also important, because we're going to have a problem in substituting our fossil fuels. So this problem of CO2 recycling is basically making use of the available CO2 in the atmosphere so that we can generate through chemical reactions fuels. And then, of course, those fuels create, again, CO2 that goes back to the atmosphere, but if we recycle it that way, we'll have a net zero contribution. So in this project, we're investigating the use of plasmas for doing that chemical conversion. The project also addresses the space component that is supported by the program. In Mars, the situation is very different. So actually, CO2 makes up the majority of the Martian atmosphere, and it's a valuable resource because in space, we're going to need things like oxygen and plastics, and with that CO2, we can actually generate those products. So if we have astronauts settling in Mars, they can use that CO2 to create that oxygen for breathing, to create rocket propellants. We will want them to come back at some point, probably. And also materials, fertilizers, nitrogen is also in minute amounts in the atmosphere, which can also be used for the fertilizer industry. This is what we call in situ resource utilization. There's mature technologies out there. One of the colleagues in the department is co-PI of the MOXIE experiment, which is now in Mars, generating oxygen. But plasma represents an alternative that has a series of advantages, we think.
So why to use plasma? So the first idea or the first advantages of any plasma technology, not only for this application that Carmen just described, are that plasma operates at low temperature and ambient pressure. So we can ignite a plasma in many different conditions. And this means that we can adapt to the local conditions. We don't need compressors or vacuum pumps. Maybe we want to use them, but we don't need. They are compatible with renewable energy sources and intermittent power, so we can start and stop operation immediately. So there is no inertia on heating, on cooling, on chain reactions, whatever. So this is very good, of course, for renewable energy. They are compact and scalable, though they don't use expensive materials. And so we can really design a prototype, and then it's very easy to scale. There is no, once the problem is solved at the prototype scale, there is no difficulty in upscaling. And they can be combined with other approaches. Sometimes even in the title of our presentation, you see the word plasma-assisted, meaning we are adding other technologies, or they can be really merged with different technologies. So, going back now to CO2, sorry, the question is, are these advantages enough to make the technology competitive? Of course, these advantages are always there, but then the question, are they enough to make the technology competitive? So what about CO2? CO2 is a very hard molecule to break. So thermodynamics plays against us. It's a very stable molecule. To break it and make use of its atoms, it's something that is always energy intensive. And that's why, or where, we start thinking in non-equilibrium plasmas. We have to try to trick nature in a way, because if we go on under thermodynamic processes, we are doomed. We will never manage to do it in an efficient way. So why then plasmas? Because plasmas transfer energy to the free electrons. So electric fields are very good, accelerate the electrons. They gain energy very fast, and then the idea is to use selectively this energy. So the first image that we have is the electrons are gaining energy, collide with the CO2 molecule, and break it. If you think this is the process, you are halfway to the truth, but you are still wrong. Because this process is very inefficient from the energetic point of view. It starts the things, but it's not enough. But it's very easy and very efficient to make the molecule to vibrate. So the electrons collide and leave the molecule excited. They can also be electronically excited states, but they can be vibrating. And then if we are clever enough, we can increase the amplitude of vibration until the molecule dissociates. So the process is actually not a resonance process like it's represented here, but the image is so strong that I always like to show this picture so that we keep in mind that this is not a direct process, but an indirect process. If we think on plasma decomposition, okay, there are many different types of plasma reactors, different plasma sources, different operating conditions. We can operate with electrons with different ranges of energies. So I will not, of course, guide you through all this graph, but the important part is to see that on the y-axis you have energy efficiency, and on the x-axis you have CO2 conversion. And it's clear that the points with higher energy efficiency have a small conversion, and the points with high conversion have a small energy efficiency. So there is this trade-off between decomposition and energy efficiency, and of course, finding the sweet spot for operation in one of the most important aspects of the research. The other important message is that the highest efficiency goes on non-equilibrium excitation. So again, this idea that we avoid the thermodynamic routes, and so we open new pathways for chemistry that are not accessible under standard chemistry.
So that's sort of the component of the plasma, which is the one that we've been investigating in more detail. But to put a reactor in place, you need other subsystems. And one thing that we wanted to do through this project and that we continue working on is basically how to design such a system and optimize for the different components simultaneously. So we have our CO2 source. That could be the Martian atmosphere. It enters the reactor and it needs to be conditioned for the chemistry to take place. That can take the form of heaters or pressurizers, pumps, and whatnot. Like Vasco said, the question is what conditions would make operation of the reactor easier. Then we have the plasma source, and again, we have a variety of plasma sources that we can utilize. But finally, the plasma source, what it does, it creates a cocktail of reactive species. You might have split down the CO2 into the oxygen and the CO that you wanted, but if you just leave it there, it will recombine. So we have identified the separation stage as a critical failure mode for our concept if we don't have it. So basically, the separation stage, what it does, it continuously pulls out the oxygen, and that favors the chemistry of the reactor and helps us get that stream of valuable products. The performance metrics of such a reactor are production rate, how much valuable products we can produce, and the energy efficiency of the process as a whole. So this gives us sort of an opportunity to optimize for all of the systems simultaneously and make this technology competitive. So the first part is the plasma source, and that's really where both Vasco and I have our greatest expertise. We've been looking at the plasma from a numerical perspective to be able to determine those performance metrics as a function of the environment. So basically, whether we're on Earth or Mars, it's very different, whether we use a heater, a pressurizer. The electrical parameters, like we mentioned, there's a wide range of plasma sources we can utilize. Normally from the discharge physics perspective, that's electron temperature, number density. From the more engineering perspective, that's the energy that we put in and the electric field that we operate at. And then basically the integration constraints, because we have it as part of a system, there might be needs of another subsystem that have to be satisfied by our plasma source. So we look at this from the numerical perspective. The IST team really are the leaders worldwide in providing chemistry subsets for many of the plasma molecules that are more readily available. So we started off with their chemistry for CO2 conversion, put it into our reactor toolbox that my students have been working on for a little while to look at conversion and specific energy input for a series of test cases, different temperatures, different pressures, different technologies, and try to see in which cases the source could be competitive. But then, of course, that's a paper study. We're also working on experiments, and we've been working with this post-nanosecond discharge strategy where we apply pulses in pulse fashion very rapidly, and we've been able to get CO2 conversion both at Martian pressure and atmospheric pressure here on Earth. And it seems like the Martian pressure is a very favorable environment for this process. Then the next part is the synergy with the membranes, that separation stage. Like I mentioned before, we create this cocktail of reactive species, but that's only half of the story. If we don't do anything, we recombine to CO2, and then we've basically just wasted energy. So for that, we need to actively pull the products, and there's been work with membranes that selectively pull, for example, oxygen for such a concept, but this is a very under-investigated area of research. We proposed this concept in a paper, and now a series of groups are studying across the globe such an operation. At MIT, we have the advantage that one of our colleagues in the MECI department, Ahmed Ghanem, is an expert on the MEAC membranes, and the next step for our work is going to be combining those plasma sources to that separation strategy. And the good news, or the interesting aspect, is that there's a true synergy between the plasma and the membrane separation. First off, we are pulling out the oxygen, so we prevent the back formation of CO2. So that membrane is enhancing the plasma chemistry. But the plasma also provides some heat that is actually required for the operation of those membranes. Typically, they operate at 800 Kelvin, and you can provide that by the plasma without needing an external heating source. And so, yeah, that's the next step for us to try to combine everything together into a working prototype.
So just a few words on the impact of the work we have developed so far. So this paper Carmen mentioned has really a high visibility. So we had our 15 minutes of fame, and we are a bit everywhere. From scientific journals to popular science journals, ordinary newspapers, blogs, and so on. So it was quite fun and new experience for us. We were very proud. There was an article on Science about of our work, but also on Daily Mail, for instance. So it was interesting. We appeared in the 2022 Aerospace Year in Review. We have plenty of lectures in the most important conferences in our field, the communications to the conferences, invited lectures in different universities. We organize a few workshops, some within the MIT Portugal program, but the last one was just last month on this APS Gaseous Electronics Conference, which is the conference in our field. It was co-organized by Carmen and Tiago, my colleague at Lisbon. So it was another high-profile workshop. Tiago was mentioned, got the Fulbright grant. We participated in a podcast, science clubs, all these interesting things. Trained a lot of students. Of course, this was not with the funding from the MIT Portugal program, but it's as a consequence of the work that we have done. New sponsors from NASA programs. So the things really are taking off, and we are very happy with this collaboration. Just a final slide with a brief mention to what next. So we are claiming and showing that plasmas are a very versatile technology for molecule conversion with applications to space and to sustainable chemistry. I'm a bit late, so I will not read exactly. Okay, so I have authorization. So we can, on space, we can focus on this in situ resource utilization, but also plasma medicine. We don't have a pharmacy if we think a colony or a spaceship, so it's used for that. Waste treatment, water decontamination. These are all plasma technologies being developed on Earth and struggling to be competitive on Earth, but on a space environment, they are much more competitive for these reasons. Yeah, we don't have these things there. We have for sustainable chemistry, CO2 valorization, what we are doing, but also nitrogen fixation for fertilizers, energy storage, and green fuels, production of hydrogen and ammonia, for instance. As Carmen said, the separation stage is still challenging, and although there is always work to be done optimizing other components, this is the real challenge that we face now. But the take-home message from us both is that we didn't know each other before, and the MIT Portugal enabled and catalyzed a new and a vibrant collaboration that we are very happy to be here to share with you. Thank you.
Thank you.
Thank you, Carmen. Thank you, Vasco. Guerras. We have some time and space for some questions from the audience, from the first presentation and for the second one as well. I don't know if anyone want to put a question. Yeah. Can you give your mind?
So I guess this is a question for the nitrogen control. So do you have plans, or do you want to talk about how you're planning to test the system before you get into the parabolic airplane? Because you only have 20 seconds once you're there, right? So how are you going to validate your system, and then do you have a test matrix plan for the flight test?
So one of our first, due to time constraints, we are only validating the system through software, but we wanted to make a test bed with, how do I call it? It's like a test bed for that has puffs of air that counteract the gravity force, and then I can test 3 degrees of freedom, and then I can rotate the ball sideways and then test the other axis. That's one way of doing it. Another way that we can also do, that's not the best approach, but it can work, is having the ball hanged from the ceiling. So at least we can test with a pulley system, so at least we can test some of the forces that are being introduced. But of course, the main topic is to test under the microgravity experiments in the parabolic flights.
We will carry out also tests inside the lab with the net. The laboratory is already prepared for aerial robotic systems, so we will try to prepare ourselves for the parabolic flight.
But you have a 2-axis air table that can check every...
Yeah.
I mean, it's fine to do the computation, but if
I know.
the performance of a thruster is not right, then
I know. It will be challenging.
Yeah. No. It's normal, but you do have an Airtable plan or something like that.
Yeah,
So all the hardware will be validated, because it's having done a lot of tests like this. You only have 20 seconds once you get in the airplane, so you need to make sure everything's working, right? Yeah. So good.
Thank you, John, and thank you. Anyone? Any more? Because I have some questions myself, especially for Carmen and Vasco, because I actually noticed that I read your paper on the science, and I didn't notice that you are the authors. So and in that time, because I'm not an expert in the area, but when I read the note in the science about your work, I was imagining that maybe this could be a kind of a research line or solution for climate change, something like that. Is that, I imagine that is super far away from that goal, but is that possible to bring a new research line in that aspect, like using the CO2 that we have?
Well,
It's okay. That's a great point. What's the chicken and what's the egg, right? In this context, the reality is that there has been a lot of investigation for the sustainability application here on Earth. So that's sort of all of the papers and work in the field has been going towards that goal. And this was sort of a new application of the same technology, with the good finding that the Martian conditions actually are very favorable for the plasma to take place. And Vasco and his team, they actually have some experiments very early on demonstrating that the Martian environment is favorable for this chemistry.
So in fact, we started from that point. In fact, so we were working on CO2 conversion for Earth. I just warn, I think all of us here understand this statement. There is no magic solution for climate change. There are many components that together hopefully will help us to handle this problem, and this is one of them. And there was, as Carmen was saying, many groups working on this, and us in Lisbon, we were also on this effort. And then, it started from there. Then it was the moment where I know precisely the moment, but where we had this notion, okay, maybe we can adapt this to the Martian environment, and suddenly we start realizing that everything that makes it difficult on Earth and less competitive with other technologies, on Mars, up to now, what we are seeing is that it's the opposite. It's a plus on the Martian environment, and so the focus and this visibility that this work is having is in part due to this, because it looks like it can be a winning technology.
Yeah, funnily enough, plasmas are much easier to produce at low pressure than high pressure. So a lot of the validation studies of chemistry, the experimental data available is for the low pressure environment. So that information is out there, but it just wasn't the focus initially.
Yes?
Do we have time for one more question?
Yes.
Renat,
Yes.
it's from me for Vasco and Carmen. It's amazing, absolutely amazing to see. We are just starting our project. We are in the middle. You already finished, and I just wanted to ask you. It's amazing the impact, and I just wanted to ask you. This was started as an exploratory project, correct?
Yep.
It's amazing the impact, the students, the everything. So congratulations on your work.
You will do the same.
Yeah.
Hopefully.
Yeah, I mean, it's
Thank
just
you.
about connecting the people, right? So this is what really is the great opportunity, connecting our two teams. But thanks to connecting our teams, I think Vasco got more connections in the US, and I got many more connections in Europe. So it's sort of, it's a catalyst. That's the word he used, and I think it's really the true value of this sort of programs.
And how interesting it is, the space resources topic. And once again, it's correlated and related with human spaceflight and robotic exploration. So it's really interesting and something that Portugal needs to increase the funding for that topic. So congratulations once again.
Same to you.
It's exciting to see all the results.
Well, I think we are past our time, but I think we have more time for final question from the audience, if anyone. No? Okay, well, thank you, all the speakers, thank you. And now we have